Hi there, my name's Isaac. I'm a tutor here at CWI. Today I wanted to go over rotational motion. Up until this point in the semester, we've mainly been studying linear motion, and it turns out that a lot of the stuff that we learned in linear motion carries over to angular motion. There's only a slight difference, and there's actually a really cool algorithm for changing equations from one to the other. So for example, we know that x in our class typically represents displacement. While in angular motion, we have theta as the angular displacement, which makes sense, right? Because when you're, for example, if my arm is rotating, the point right here has a lower linear velocity than here. This one's traveling further over the same amount of time, so this has a higher linear velocity than this, but they both have the same angular velocity or displacement. So v is velocity in linear, and omega is angular velocity. A is acceleration, alpha is angular acceleration. Force is F, and a rotational force is known as a torque, and we'll kind of go over that. There's definitely some different rules. And then mass translates to moment of inertia. And moment of inertia is kind of a challenging concept to grasp. Actually, all of this angular stuff can be kind of tricky. There's still a lot to learn about it. But what I wanted to focus on here was firstly writing equations from one form to the other. And then also I wanted to focus a bit on moment of inertia because I feel like that's a vital concept. So I have this kinematics equation here that we learned for linear, and I just wanted to point out how we can rewrite it using this algorithm. So 2 stays as a 2. Acceleration will become alpha, or angular acceleration, 2 times alpha. Then we have our displacement, which goes from x to theta. Alright, it's delta theta, equals vf squared. Well, v will go to angular velocity, or omega. So this will be omega final squared minus omega initial squared. And you can really do this with any equation. It's pretty amazing that it works this way. So one of our famous equations, sum of force equals mass times acceleration. We just go to our conversion chart. If we want to write this in terms of angular motion, we can change the force to a torque. So sum of torques equals mass, which in rotational motion is moment of inertia, times acceleration, which will change to angular acceleration. So mass, when we're talking about point-like objects or even just linear motion, is basically a material or an object's resistivity to change in its linear motion. So the heavier a mass is, the more force you'll have to put into it to accelerate it. Whereas the lighter mass is, it's the opposite effect. The less force you need to move this object at a certain acceleration. It's a little bit different in rotational motion because when we think about it, let's imagine that we have 2 different kinds of doors. So let's say that we have kind of like a saloon door. You know, those saloon doors, they're really quite easy to open. So if I was going to push this door open, it would be relatively easy to swing open. Now, what if I have a door that is a solid core, 36-inch wide door, and I'm going to open this? It's going to take a lot more force to open. And so the point here is that not only does moment of inertia rely on the distance from the rotation axis. So with this big door, our rotation axis is here around the hinge. With our little door, our rotation axis is here around the hinge. Well, you'll notice that for the little door is that it has a smaller radius around that rotation than, for example, the big door does. This has a larger radius. And of course, we've gone over this, the big door, because it's solid core and it's larger, is going to have a larger mass as well. So we know that mass isn't the whole picture when it comes to rotational inertia, right, our moment of inertia. It has to do with not only the mass, but how far that mass is from the axis of rotation. So, let's look at another idea. So what if we have a little cube of a certain mass m, and then we have a long and ductile, so we've taken this cube of equivalent mass, but we've pounded it into a long, thin rectangular rod, has the same mass, and I'm going to draw an axis of rotation. So I'm going to try to rotate these about their center of mass. Well, the question is which one would have more resistance to that rotation? And you can test this for yourself, but it turns out that the long rod that's been pounded out, because it has the same mass, but more of that mass is a greater distance from the axis of rotation, where with the small cube of the same mass, its mass is closer to the center of rotation, to the axis of rotation. So it turns out that there's a nice formula for this that describes the importance of the mass itself and how far the mass is from its axis of rotation. And we're going to start with point-like objects. So the moment of inertia for some point-like arrangement is going to equal to the sum of the mass, the point-like mass, multiplied by the distance from the axis of rotation that mass is squared. So let's go ahead and take a look at an example. Let's say that I want to rotate this system of masses about this axis, and I have a mass, I'll call it mass 1 over here, at a distance r1 from the axis of rotation, and then maybe I have a mass 2 that's down here, that's r2 distance from the axis of rotation. So we're measuring from the axis of rotation, which is something that we get to choose. We could want to rotate it about this axis or this axis. We get to choose the axis. So the moment of inertia of any system of point-like masses is entirely dependent on what you want to rotate it about. So if I were to write out this sum long form, I would have, well, m1 times r1 squared plus m2 times r2 squared. And this would give me the inertial resistance. In other words, this will give me the moment of inertia that if I want to come and spin this, system of particles, it will resist me to a certain extent based on its rotational inertia. It wants to stay still. It doesn't want to rotate. You have to apply a force to cause it to rotate, which is actually a torque in rotational motion. So, anyways, this is for point-like objects. It's pretty nice. It's an easy algorithm. Another important thing to remember is that if we're in 3 dimensions, for example, and I have a mass, let's say it's up here, it's a certain amount in the x, certain amount in the y, and a certain amount in the z, and I want to rotate it about, let's say, the z-axis. The distance that I will put in for r is not going to be the distance it is from the x-axis, or the distance from the y-axis, or the distance it is up from in the z direction. The distance that we use for these radiuses is the shortest possible distance between the mass and the axis of rotation. So you always choose the shortest possible distance. I'm not going to choose longer distances that take me to the z-axis. So I want that radius to be orthogonal with the axis of rotation. So that's an important thing to remember. Turns out we can write this in calculus form by saying, let's imagine that I have a continuous object, and for now we'll say it has constant density, constant volume density. I could write this as an infinite sum as the integral of r squared dm, where r squared is the distance that the small chunk of mass is from the axis of rotation. So let's say I want my axis of rotation to be here, and I'm going to look at my small little infinitesimal chunk of mass over here, dm, and this r squared is going to represent that orthogonal shortest distance from dm to the axis of rotation. Now this isn't so important in this class. In Calculus 3, we go over this and we learn several ways to do this problem. But I just kind of wanted to point this out, that we can actually calculate the moment of inertia for objects even that don't have uniform density. But in this class, we're mainly going to be focused on objects that have already been solved for. So for example, here's a few objects that have already been solved for. We know that a long, thin rod, if we rotate it about its center of mass, so I'm rotating about its center of mass, I know that the moment of inertia that's occurring here at the center of mass for this long, thin rod to be rotated in this direction is equal to 1/12 times the mass of the rod times the length of the rod squared, assuming that the mass density, right, assuming the density is constant throughout the whole rod. Or another example would be a thin disk of a given radius. So we're assuming this is a very thin disk. You'll find that you'll use this a lot during pulley problems. So it has some given radius, and it has some mass, and the moment of inertia to rotate it about this axis around the center of mass is equal to 1/2 the mass of the disk times the radius squared of the disk. So these have already been solved for us, so when we're looking at problems, we don't want to have to derive every moment of inertia. There are tables in the book, there's tables online, so I highly